Welcome to part 2 of our series on reliability engineering for semiconductors and microelectronics, presented by SLAC Center of Simulations and Reliability Engineering. Refer to part 1 for introduction and background information. In this section, we will explore the electromigration failure mechanism. Understanding this is crucial for enhancing the reliability of semiconductor devices. Electromigration is a reliability phenomenon in which high current density causes metal atoms in interconnects to gradually move over time. This atomic migration can lead to void formation, increased resistance, and ultimately open circuit failure in electronic devices. To mitigate electromigration, electronic devices are designed using well-established design rules that limit current density, control operating temperature, and select appropriate interconnect materials and geometries. Reliability models and accelerated testing are used to ensure that interconnects meet required lifetime targets under expected operating conditions. Electromigration lifetime is commonly described using Black's equation, which relates the mean time to failure, or MTTF, to operating conditions. In this model, MTTF decreases with increasing current density and temperature, reflecting the fact that higher electrical and thermal stresses accelerate atomic transport in metal interconnects. Black's equation includes a current density exponent that captures how sensitive a material is to electromigration, and an activation energy term that represents the temperature dependence of atomic diffusion. Together, these terms allow engineers to predict interconnect lifetime and design devices that meet reliability requirements under normal operating conditions. Here, we walk through an example of Reliability Demonstration Test, RDT, planning for electromigration. The objective of this test is to demonstrate reliability of 95% with confidence of 50% for 10 years of use under the following operational stress profile. Standby. Operation. 4,000 hours per year at a current density of half of the max rated current density and a temperature of 50 degrees C. Nominal operation. 3,000 hours per year at max rated current density and a temperature of 50 degrees C. We would like to understand our sample size and test duration. We begin by calculating the acceleration factors using the shown stress conditions. Using Black's equation, we compute separate acceleration factors for standby and operational conditions. Standby acceleration factor is 25. Operational acceleration factor is 6.26. These acceleration factors are then used within our reliability modeling tools to determine the required test duration and sample size needed to quantitatively demonstrate the target reliability for the transistor under real-use conditions. We use ReliaSoft Weibull++ software for our test design and data analysis. The important note is RDT cannot answer lifetime questions. In other words, RDT only shows we pass certain reliability requirements under given use stresses. But if we change the stress conditions, we need to rerun the RDT campaign. This is a major drawback for RDT, and lifetime testing in these cases becomes essential. There are two common ILT methodologies. Single stress ILT. In this approach, components are tested under a single elevated stress condition until failure. The resulting data provides the lifetime under that specific use stress. However, if the actual operating conditions vary, the test may need to be repeated to capture different stress scenarios. The graph on the right shows an example of ALT results under a single-use stress condition. Multiple stress ALT. A more rigorous approach uses 3 or more stress levels to generate a life stress relationship. This relationship allows us to predict component reliability across a range of use conditions without retesting, as long as the system properties remain consistent with those of the test units. This method is particularly effective for building reliability models that can be applied to real-world operating conditions. The graph on the left shows stress life ALT result. Let's walk through the accelerated lifetime testing plan step by step. Step 1. Define the main stressors. First, we identify the key stressors that will drive failures during the test. In our example, these are temperature and current. Step 2. Define the life-stress relationship for each stressor. Next, we determine how each stressor affects component lifetime. Temperature is modeled using an Arrhenius relationship with a use temperature of 50 degrees C and a maximum test temperature of 80 degrees. Current is modeled with an exponential relationship, where the use current is 4 milliampere per micrometer square, and the maximum test current can go to 8. Step 3. Select the ALT test plan. For this example, we choose a 3-level optimum test plan, which allows us to efficiently generate lifetime data across the defined stress levels. Step 4. Estimate failure probabilities at the end of test time. Using the stress levels, we estimate the probability of failure after 100 test hours. At use conditions, we set the probability to 0. At each maximum stress levels, while keeping the other stressor at use condition, we set the probability to 50%. Step 5. Define lifetime distribution and confidence level. We use a Weibull distribution with beta equals 1 to represent random failures and set the confidence level at 80%. Finally, these parameters guide the number of samples, stress levels, and sample allocation required to quantitatively generate the stress-life relationship. Failure data generated through accelerated lifetime testing can be used to develop stress-life reliability models. First, the ALT data is compiled by recording the time to failure along with the associated stress conditions, such as temperature and current, for each test unit. Next, an appropriate stress transformation law is assigned to each stressor based on the underlying physics of failure. For thermal stressors, an Arrhenius relationship is used, typically expressed through a reciprocal temperature transformation. For non-thermal stressors, such as current or voltage, a logarithmic transformation is commonly applied, consistent with inverse power law behavior. Once the stress transformations are defined, the model parameters are estimated by fitting the data using standard statistical methods. Two commonly used approaches are maximum likelihood estimation, which provides statistically robust parameter estimates, especially for censored data; least squares rank regression, which offers a simpler, graphical fitting approach. Together, these steps allow ALT data to be translated into predictive reliability models that can be applied across a range of operating conditions. As shown in the pictures, we use ReliaSoft software to convert stress-life data into reliability models that can be used in our fault tree analysis. Next, let's examine thermal cycling failure mechanisms in microelectronics. As devices experience repeated temperature changes during operation, mismatches in material properties, particularly coefficients of thermal expansion, generate differential thermomechanical strains within the package and interconnects. Over time, these cyclic strains accumulate as fatigue damage, leading to crack initiation and eventual failure, and therefore setting the limit on device lifetime. To address this, we design thermal cycling tests that intentionally accelerate these fatigue mechanisms under controlled conditions. Let's now look at how these tests are defined and how they are used to evaluate and qualify device reliability. Using our transistor example, particularly in power, RF, and high-performance ICs, devices experience repeated self-heating and cooling during each power cycles. This results in a temperature swings across the device and its interconnects. In addition to operational cycling, diurnal and seasonal ambient temperature variations can also introduce thermal cycles that contribute to accumulated fatigue damage. The primary thermal cycling failure mechanisms include fatigue of metal interconnects, fatigue of solder joints or micro bumps, especially in flip chip and 2.5D and 3D ICs, bond wire fatigue, commonly observed in power transistors and legacy packages, dielectric cracking, particularly in advanced technology nodes, and heterogeneous integration. For thermal cycling-driven failures, the mean time to failure is commonly described by the Coffin-Manson relationship, a power law model in which lifetime decreases with increasing temperature swing. In this model, the exponent n represents the fatigue sensitivity of the material and interconnect geometry. Now, let's walk through the thermal cycling reliability demonstration test design steps. Our objective is to demonstrate R95 C50 reliability for 10 years of use under the following operational stress profile: 10 power cycles per day. Temperature swing for each power cycle is 50 degrees C. To evaluate thermomechanical fatigue in semiconductor devices and PCB assemblies, industry standard test methods such as IEC 6068214 and GDEC JESD22A104 are commonly used. These standards define power and temperature cycling endurance tests that are designed to accelerate fatigue damage while preserving the underlying failure physics. The acceleration factor for thermal cycling is calculated using an inverse power law relationship consistent with the Coffin-Manson fatigue model, where lifetime scales with the temperature swing raised to a material-dependent exponent. Once the acceleration factor is established, the ReliaSoft software reliability demonstration test (RDT) design module is used to determine the required number of samples and test duration needed to quantitatively demonstrate the target reliability at the specified confidence level. Okay, now let's switch gears and talk about thermal shock. A thermal shock event is characterized by a rapid and large temperature change that occurs over a very short duration, much faster than the gradual changes seen in typical thermal cycling. For example, if a device goes from room temperature at 25 degrees to an outside temperature of 10 degrees C in a matter of seconds, that sudden temperature swing can produce intense internal stresses. Unlike thermal cycling, which induces fatigue over many slow cycles, thermal shock exposes a device to abrupt temperature transitions that can exceed the mechanical limits of materials and interfaces. Rapid heating or cooling leads to differential expansion or contraction between dissimilar materials inside the device, such as silicon, metals, and PCB laminates, because these materials have different coefficients of thermal expansion. When these differential strains occur quickly, they can cause cracks, delamination, fractures, or other structural failures that occur immediately, not just accumulate over time. Thermal shock testing is widely used in reliability engineering to simulate worst-case environmental conditions. By exposing components to quick thermal transitions, engineers can identify weak points that might fail in real-world applications where sudden temperature changes are possible, whether due to environment, processing, or power cycling. A robust design should be able to withstand expected thermal shock events without compromising structural integrity or performance. Thermal shock induces severe temperature gradients, either within a single material or between dissimilar materials in an assembly. These gradients can arise from events such as cooling systems being rapidly switched on or off, or from environmental transitions including air-to-air or air-to-liquid thermal shocks. Unlike gradual thermal cycling, thermal shock events introduce high transient stresses that can exceed material and interface strength limits. The primary thermal shock-induced failure mechanisms include fracture of metal interconnects, fracture of solder joints or microbumps, particularly in flip chip and 2.5D 3D ICs, bond wire fracture, commonly observed in power transistors and legacy packages, dielectric cracking, especially in advanced technology nodes and heterogeneous integration. Because thermal shock failures are often strength-limited and catastrophic, device reliability is typically evaluated using pass-fail criteria or survival probability, rather than a conventional mean time to failure. Thermal shock testing is therefore used to verify that a design can withstand specified shock conditions without immediate failure, ensuring robustness under worst-case operating and environmental scenarios. Now let's design a repetitive thermal shock test for our transistor device. The objective of this test is to demonstrate R95C50 reliability for 10 years of use under the following operational stress profile: 5 thermal shock events per day over the entire service lifetime with temperature swing of plus 40 degrees C to a 10 degrees C. To evaluate thermal shock robustness in semiconductor devices and PCB assemblies, IEC 6068214 is a widely used industry standard. This standard defines controlled thermal shock test conditions designed to expose devices to rapid temperature transitions representative of worst-case environmental and operational scenarios. For reliability assessment, the acceleration factor associated with thermal shock severity can be estimated using an inverse power law relationship, consistent with strength and fatigue-based failure models. Once the acceleration factor is defined, the reliability demonstration test, RDT, design module is used to determine the required sample size and test duration needed to quantitatively demonstrate the target reliability and confidence level. Now let's briefly discuss corrosion failure mechanisms in microelectronics, an important environmental reliability concern. Corrosion in electronic systems is driven largely by moisture and humidity. One of the most common forms of corrosion is galvanic corrosion, which occurs when dissimilar metals are in contact in the presence of an electrolyte. Another mechanism is electrochemical migration, where metal ions dissolve and migrate under an electric field in the presence of moisture. On PCBs and solder joints, corrosion can induce material swelling and deformation. The commonly used moisture temperature corrosion, humidity, reliability model is called the PEC model. RH is relative humidity, T denotes absolute temperature in Kelvin, IA is the activation energy, N is humidity exponent, and K denotes Boltzmann constant. IEC 6068278 is a widely used standard for corrosion testing of semiconductor devices and printed circuit board assemblies. As discussed previously, the acceleration factor for moisture-driven corrosion can be calculated using Peck's law, which accounts for the combined effects of temperature and humidity. Once the acceleration factor is established, a reliability demonstration test, RDT module, such as those available in ReliaSoft, can be used to determine the required number of samples and test duration needed to quantitatively demonstrate the target reliability and confidence level. In this session, we presented an integrated reliability engineering approach for semiconductor and microelectronics product lifecycle management. We began by discussing practical reliability engineering principles for microelectronic devices, emphasizing the importance of understanding dominant failure mechanisms and identifying risk early in the design process. We then introduced reliability modeling as a system-level framework for capturing critical failure paths and complex interactions that are not always visible through component-level analyses alone. Next, we walked through reliability test planning, showing how accelerated testing, such as electromigration, thermal cycling, thermal shock, and corrosion testing, can be used to generate meaningful lifetime data within practical timelines. Finally, we demonstrated how reliability test data is integrated into system-level reliability models, enabling quantitative predictions that support informed design decisions and robust product qualification. Together, these elements form a closed-loop reliability methodology that helps ensure microelectronic systems meet performance, lifetime, and mission requirements throughout their operational life. Thank you for your attention. At the SLAC Center for Simulation and Reliability, we are committed to developing cutting-edge technologies that advance science and enable practical engineering applications. We hope this session has provided valuable insights into reliability engineering for semiconductors and microelectronics.